High-end 3D renders often fail during the import process, causing complex light and smoke simulations to glitch and flatten out into a low-contrast image. This loss of fidelity occurs when 8-bit sRGB color processing meets destructive tone mapping applied inside the 3D render engine. Highlights require significant headroom to maintain their physical properties. When the data reaches an 8-bit limit, the curve flatlines, destroying the raw math of the render before it reaches the compositor. Maintaining this data requires a strict export constraint: 16-bit or 32-bit float EXR sequences, with all render engine post-effects disabled. Processing this 32-bit data requires ACES-CG, a scene-referred linear working space that preserves the full range of the render. Standard grading tools like Lumetri are designed for display-referred footage. When applied directly to linear ACES-CG data, these tools behave unpredictably, often leading to clipped highlights and distorted color balance. The Lumetri sandwich bypasses this issue. A node translates the linear ACCG stream into logarithmic ACCCT, allowing for intuitive, precise color adjustments without breaking underlying data. A second node then returns the signal to ACCG, ensuring subsequent effects occur in a physically accurate linear environment. Establishing this 32-bit ACCG pipeline is the first requirement. Without it, the math behind simulation integration and relighting will remain compromised. Professional workflows rarely rely on a 3D engine's default duty render. Instead, the compositor uses arbitrary output variables, or AOVs, to access the individual physical components of the image. The beauty pass is rebuilt using an additive equation. It starts with the diffuse pass as the base layer, providing the core color and lighting. Isolating the specular pass allows independent control over highlight intensity, sharpening reflections without affecting the base brightness. Separating reflection and refraction passes makes it possible to tune how the object interacts with the background plate, adopting environmental lighting. The shadow AOV grounds the object in the scene. In an ACES workflow, applying this pass with a multiply blend mode ensures the shadow intensity matches the ambient light levels of the footage. Targeting specific elements for adjustment is handled by cryptomatte passes. This standard generates accurate masks for every object and material, removing the need for manual rotoscoping. Rebuilding the beauty pass manually gives the compositor active control over light, shadow, and texture. Production often requires lighting changes to a 3D object long after the primary render has finished. Rather than re-rendering the 3D scene, compositors use the normal pass to execute relighting directly in the timeline. Every pixel in a normal pass encodes the physical XYZ orientation of a surface into the red, green, and blue color channels. This equation translates surface data into interactive light. It calculates the relationship between the surface orientation and a virtual light source. The variable n represents the surface normal, derived from the RGB data. The variable L is the vector toward a virtual light source created within the compositing software. The math generates precise rim lights, sharp specular hits, and shadows natively in 2D space. Vector relighting removes the need for 3D software during final lighting adjustments, allowing for immediate, seamless creative revisions. Managing dozens of AOVs and relighting effects within a traditional layer stack often results in an unmanageable and fragile timeline. Complex motion graphics and simulations require a transition to node-based procedural workflows. Node architecture replaces vertical stacking with lateral logic. This allows a single data node to drive multiple properties at once. For example, one noise generator can control both particle turbulence and light flickering. This procedural environment allows for the integration of open VDB volumes. Importing VDB caches allows massive, heavy smoke and fire simulations to be manipulated directly through the compositor's camera. Technical management of VDBs requires balancing voxel resolution against calculation time to maintain performance during playback. Assigning volume materials to these VDB nodes provides the parameters for light scattering and absorption, which are necessary for physical accuracy. Proceduralism changes the focus of the composite from manual keyframing to the precise engineering of fully automated visual systems. AOVs and volumetric simulations will fail to integrate if they appear to float or slide over the background footage. 3D camera solving provides the physical foundation for anchoring these elements. Using an inverted NASC prevents tracking errors by ensuring the solver only analyzes rigid architectural planes while ignoring moving subjects. Tracked planar data can be converted into a physical 3D mesh, which acts as a shadow catcher within the composition. Integrating graphics onto non-rigid surfaces, such as skin or cloth, requires sub-pixel tracking. Power Mesh utilizes inverse stabilization to mathematically flatten a deforming surface, allowing for the precise application of 2D graphics. Once the graphic is applied, the recorded wrinkles and physical movements are reapplied to the layer, locking the detail to the organic surface. Sub-pixel tracking data provides the physical constraints necessary for believable integration. Traditional 8-bit layer stacking and baked beauty renders are insufficient for current production requirements. Modern title sequences rely on 3 pillars: 32-bit ACES CG discipline, advanced node-based proceduralism, and data-driven match weaving. Adhering to this specific, highly technical architecture ensures that your 3D renders and 2D composites become completely technically indistinguishable from reality.